Here's the topic, morphometrics. Now we'll describe what it can do for us. The little squares in this figure are landmarks. We can use a set of those to represent a structure in 3D space, three-dimensional, 3D. The more landmarks, the closer that set can approach thoroughness. For structures that aren't always constant, the landmarks will move. If we keep a record of their location, then a compilation of the variations contains important diagnostic clues. If the variations are much smaller than the landmark coordinates, we can use a linear model to quantify what's happening in terms of shape states. Shape state analysis can describe multiple structures of similar types or the same structure at different periods of time. Each set of landmarks in a group might be from a 3D X-ray image, a cone beam scan, from a patient, or every landmark set could come from one structure, each at different times in a sequence. Since landmarks can migrate independent of one another, the centroid can also move. Every landmark always remains attached only to the centroid by weightless connecting arms that aren't quite rigid. We can look at those landmark sets in a number of ways, for example, from a top view, from the front, or the side, to describe what happens to the structure. Of all the changes that can occur, a 4x4 matrix is able to determine these important ones: translation, rotation, scaling, and shear. The matrix can also express perspective effects, but that isn't any help in structural analysis. An excellent book by Rogers and Adams, cited in the manuscript, explains that the 16 elements of a 4x4 matrix reduced by 1 produces a homogeneous transformation with 15 independent elements. That consists of 5 degrees of freedom in each of 3 orthogonal directions and, omitting perspective as just explained, will investigate 12 total degrees of freedom. All of us understand translation along X, Y, and Z directions, plus rotation about those axes, but scaling calls for a little different added interpretation in this context. If every coordinate of every landmark expands or contracts by the same percentage, that won't affect the shape. So we'll subdivide the 3 scaling degrees of freedom into 1 equal in all directions plus 2 unequal. Adding the equal scaling one to 3 each for translation and rotation gives 7. That leaves 5 for shape. The Rogers and Adams book just mentioned gives further detail and also offers more descriptions for shape states. For example, in 2D, unequal scaling would change a square into a rectangle, and shear would change a rectangle into a parallelogram. So, for shape analysis, the first step is to define a landmark set to be used as a reference. For a group of patients, that can be formed by averaging. For a structure, the reference can be the landmark set at one designated time. Then here's how to compare all members of the group versus that reference. First, translate each member's centroid to the centroid of the reference. Then divide each member's coordinates by its root sum square, so that the sum of squares of the resulting coordinate set is just 1, dimensionless. Then rotate each member about all 3 axes in a way that minimizes the sum of squares of departures between its own landmark coordinates and the corresponding ones in the reference. Those 3 steps produce a Procrustes representation of the structure. Here we describe the effects of extracting the remaining 5 shape states for application to medical imaging, plus early warning for earthquakes and infrastructure failures. The last video from the link shown here offers more detail for the medical imaging application. For medical imaging, it was mentioned that a reference shape can consist of a landmark set formed by averaging. The 2 image sets I'll describe are for the windpipe and the pallet. The windpipe coordinates were averaged over a full set of landmarks from that group. The pallet group, though, included a majority of abnormalities, with cleft pallets. To compute that reference, only the normal patient's coordinates were averaged. This slide for translational shift, with the normal members at the right in black, easily justifies that decision. These and also later plots have different symbols, circle, square, triangle, for different directions, but here the intent is to cover only the method and to show that it works. For the details I've omitted, the one to contact is University of Hawaii Professor Scott Lozanoff. Now the rotations, with a plus sign added for the dominant quaternion element. Again, only the normal subset on the right looks normal. Landmarks from a Procrustes representation of different individuals tend to cluster together. For both the windpipe and the pallet groups, here you can see views from each of three directions, before and after extraction of the deformations due to the 5 shape states. If we had a perfect deformation model, the right half from each group would look more like a collection of discrete points instead of just smaller clusters. Still, the shrinkage in cluster dispersion is plainly evident. In some of these cases, the variance was reduced by 90%. 90%. Significance of that is illuminated especially by comparison versus only 19% documented by the pioneer who first derived the deformation extraction technique. So why was I able to get so much more variance reduction than that pioneer? Because his math is limited to 2D. The physical world is 3D. I use 3D representation throughout. Before leaving the medical imaging application, one more graphical technique is worth showing. A plot is made for the departure of each landmark's theoretical placement, according to the 4x4 matrix model, from its location indicated by actual measurement. That difference is plotted for every group member at each landmark index and for every landmark at each group member index. This plot shows, for example, the most severe deformation occurring at landmark number 3 for pallet patient number 16. Second and third most severe are for pallet patient number 18 at landmarks number 3 and 4. Now our attention shifts to another application, validated by data recorded before the earthquake that devastated Japan in 2011. Let me preface this with a note about the perceived state-of-the-art in earthquake prediction. It's widely considered an unsolved problem. Recent quotes from authoritative sources have stated a need for advanced warning expressed in seconds. You are about to see dispersion from recorded GPS data showing evidence several days in advance. How much future promise that holds is yet to be seen, but the stakes are sky high, and we're looking at expansion of advanced warning time from seconds to days. Okay, here's the landmark set chosen by Ohio University Professor Frank Van Grass, who also gave me precise landmarks from them. The numbers available from station recordings weren't accurate enough. He corrected those and gave me the refined values. Without his corrections, my results would have been inconclusive. Here's one of the planar views of the landmark set on one particular day. In this application, the reference shape was chosen as that set on day -29, a little over 4 weeks prior to March 11th, 2011. Pre-shocks are a familiar indication that a quake is brewing, but they don't say where. A later slide will get to that, but first, this slide shows clues well in advance. Very noticeable at day number -16, and extremely strong on day number -5. The source of this clue was sensitivity to rotation below and above amounts used for Procrustes representation. Another clue comes from sensitivity to the direction of rotation used for Procrustes representation. A rotation axis can be tilted in each of two different directions, so this sensitivity is plotted against both of those directions. We start here at day number minus 28, when things differ only a little from the reference conditions one day earlier. For the next day, we see a little more difference, and we'll continue the countdown one more day at a time. Minus 26, minus 25, minus 24, minus 23, minus 22, 21, 20, 19, 18, 17, 16. That's a much bigger jump than normal. But then it goes back down at minus 15. Continuing now, we're seeing more action. Minus 14, 13, 12, 11, 10, 9, 8, 7, 6, 5. How about that, sports fans? Then it becomes less dramatic again for a few days. Minus 4, 3, 2, until day number minus 1. One more before the blast. Okay, so far these results aren't about location, and I promised to address that, which is considered by almost everyone as an unsolved problem. It will be helpful to recall what we saw a few slides ago for day number minus 5. Clearly something is brewing, but where? Now recall the last plot for the medical imaging application and realize that instead of different patients, now we have different days pre-quake. On each day we have, at each landmark, all transformation elements from Procrustes scaling, rotation, and centroid translation. We also have the shape states computed from the deformation program. Using all those values, a theoretical landmark set is available to form comparisons between the model and the measurements. Here the differences are plotted for all landmarks on each day. Initially, there's a nominal dispersion of 2 centimeters, but as time advances toward the quake event, more activity becomes noticeable. Because of what we saw before about day number minus 16 and minus 5, larger differences along the 2 vertical lines are not surprising. Aside from those, plus 2 more values exceeding 2 centimeters by modest amounts, attention is drawn to the points that I surrounded by a small red square. Here's the reason why I did that. They're for the landmark closest to the epicenter. Shortly after the first clue from day number minus 16, they begin to form an above dispersion pattern. By the time day number minus 5 is reached, the pattern is well established, even though on that day we couldn't yet access data to the right of that last vertical line. No declaration is made here that every earthquake will offer the same capability, but this happened with the first attempt to use shape states for advanced warning. Further details are available from the links cited. With data from monitoring stations already in existence, the cost of processing the station data and distributing the results would be negligible compared to the value of a 5-day notification. That last statement applies to another operation, infrastructure monitoring. Unlike the 2 preceding applications, this is one where I can't offer any experimental data. Another difference, though, is compelling. Here we can use shape state analysis for prevention. If anyone doubts that prevention is needed, the link on the last line cites a 60 Minutes program that showed the dismal condition of our infrastructure. Just for bridges alone, structural integrity is questionable for over 70,000 in the U.S. There won't be a budget allocation anytime soon to repair 70,000 bridges, plus God only knows how many more other structures. We need to know where failure is imminent. Here's a way to get that. Structures change shape before they collapse. This method enables continuous tracking of slow migrations to indicate reinforcement only where it's needed, using whatever GPS receivers, LiDAR, strain gauges, etc. are there, already deployed in many cases, to run the deformation calculations all day, every day, and transmit results at low cost to a control center. The capability exists, although hardly anyone realizes that. So, what's to be done? I'm only one guy. What's needed here is a super capable honcho who understands both the technical side of this and the administrative side, which I don't know anything about. I plead incompetence. In addition, that super honcho needs to have the right motivation. The purpose here is to solve critical problems and get people out of danger, not to become a billionaire. And finally, the one in charge should be from the kind of institution with a track record of rock-solid accomplishments. Okay, the leader must have this capability and that important qualification, plus also this admirable characteristic, and more, etc., etc. Dream on, dream on. Who can meet all those requirements? Where can we find that George Washington, Abraham Lincoln, Mother Teresa, Davy Crockett, Florence Nightingale, William Shakespeare, Paul Bunyan? Where are you going to find a leader like that? Ta-da! We have an answer. Here's the individual who delivered the earthquake data, correcting it before delivering it, thus enabling the validation. An ongoing project is already in progress under his direction. Talk to the professor for any further planning.